All right, so we were just talking about how to test for concavity, and it's very similar to how you test for increasing or decreasing, but we're using the second derivative. And this last one about having no concavity when you have a linear function, but it's not just that. Here, take a look at this picture that's right here. You can see this sort of looks like a cubic function or something like that. I'll zoom in here for a second. And you have yourself a horizontal tangent line at this particular point. And notice that on the left-hand side, this is concave downwards, and on the right-hand side, it's concave upwards. So we couldn't find an interval over which this tangent line is always up above or always down below, because it's up above on the left-hand side and it's down below over here on the right-hand side. So there's no concavity right here specifically at A, but this is a special point. It's a point that marks where the concavity changes, and we're going to define that thing as a point of inflection, as you're about to see. Okay, so once again, finding concavity or testing for concavity is just similar to testing for where our function is increasing or decreasing, but we're just going to do it on the second derivative. Take a look at this example 2 here. We want to know what are the intervals, the open intervals, over which our function f is concave up versus concave down. So we're just doing a visual inspection here. We don't have an equation that we're going to take the first or second derivative of. We just are doing a visual inspection about concavity. Okay, so I'm going to come over here, right on my picture. Here we go. All right, so I can see that my graph seems to be from A to B. Let's just take, so it's very convenient that it labeled all of these little intervals here. From A to B, this whole shape is concave down. So I'll just write that as a concave down from A to B, open interval. Okay, and then on this next interval from B to C, this is curving upwards here. If I put in some tangent lines would be down below. So from B to C, I'm going to say that this part is concave up from B to C. This point right here, it has no concavity. It changes. It changes concavity from concave downwards to concave upwards, and we call that something special. We call this thing a point of inflection. And it's just where your graph changes concavity from upwards to downwards or downwards to upwards. Okay, let's take a look at the next interval from C to D. From C to D, looks like this shape is concave upwards. So concave upwards on the interval from C to D. And then what about from D to E? From D to E, it is, wait, did I say this is concave up? That is not concave up. This is going downwards. What the heck? That's okay. I can change it pretty easily. Just make that a D. Okay. Yeah, okay. So then from D to E, this one is concave upwards. Okay. All is right. All is right in calculus from D to E. Let me ask you a question. What about this point right here? This point is where we change concavity from downwards to upwards. Is this thing also a point of inflection? And the answer to that question is a big fat no. And the reason why is because there isn't actually a tangent line at this particular point, right? It would kind of teeter on that point because it's a sharp curve. So no, this is not a point of inflection. In other words, you're not going to have a point of inflection at a sharp turn. You have to have a tangent line there in order for a point of inflection to actually exist, even though you change concavity. Let's keep going, shall we? We have another interval from E to P. This looks like it is concave upwards, right? If I complete this little graph here, it's a concave up from E to P. And there's nothing special about this particular cusp. It keeps its concavity, and you have some sort of sharp turn there. Okay. And then finally, we have the interval from P to Q, and from P to Q, we have a concave down type of shape. Concave down from P to Q. And then once again, we have this special point right here at P where we're changing concavities, and there would be a tangent line here. Like if I drew in a tangent line, it'd be a horizontal tangent line, I do believe, and this one is yet another point of inflection. Okay, all right, and yeah, so here's all those intervals. Wow, all I had to do was advance it and it showed me all of the answers. Okay, so here then, let's define points of inflection based on what we were just seeing. Let f be a function that is continuous on an open interval, and let c be a point that's in the interval. We're going to say that c is this point of inflection. If the graph of f has a tangent line at that point, remember, it's not going to have a tangent line at a cusp. If it has a tangent line at this point, then this point is a point of inflection if the concavity of f changes from upward to downward or downward to upward at that point. So you can take a look at each one of these pictures here. Zoom in just a little bit. We have concave upward on the left-hand side, we have concave downward on the right-hand side, and we have a tangent line that does exist at that particular point. This is a point of inflection. Okay, over here on the bottom picture, concave downward on the left side, concave upward, we have a horizontal tangent line which exists. This is a point of inflection. And finally, we have a vertical tangent line. So the second derivative does not exist right here at this point of inflection. It's concave upward, changes to concave downward. However, it does still have a tangent line, a vertical tangent line, so it's still considered a point of inflection. So what do you think the value of the second derivative is going to be at a point of inflection? The point of inflection, the value of the derivative should be either 0 or undefined. Okay, so it's sort of like a critical number, but it's on the second derivative. You can kind of think of it as a supercritical number. That's not, anything formal. It's just something that I call it so that we have something to refer to it as. Okay, so if f comma f of c is a point of inflection of the graph of f, and then either the second derivative is equal to 0 or the second derivative does not exist at x is equal to c. And so that's how we're going to be able to tell whether or not a function has a point of inflection. That's where we're going to start, right? That's where kind of like whenever we find the first derivative, and the first derivative gives us critical numbers when we set it equals 0 or it's undefined, and that's going to break up the domain into intervals, and we're going to test those intervals to see if it's increasing or decreasing. We're going to do the same thing with points of inflection. We're going to find these quote-unquote supercritical numbers to break up the domain and test to see whether or not over each one of those intervals it's concave upwards or concave downwards. Okay, and so another test for this is just to see whether or not the second derivative changes signs at a point of inflection. Does it change from plus to minus, minus to plus? And then you want to make sure, do you actually have a tangent line at that point? Is it a sharp turn? Because if it's a sharp turn, you're not going to have a point of inflection. All right, so in the next couple of exercises, we're going to put all of these definitions into practice and all of these techniques to find points of inflection and intervals over which our function is concave up versus concave down.